I want to start off with all the other integrals that we know how to do. We have a single integral. We have a double integral. We have a triple integral. We have a line integral. How do you know that something is a line integral? It has a C. How else? Sometimes, okay, not what I was looking for. Yes, ds. Remember, that's little ds. You also could have something like this, dr. Or, like some of you just said, you could have the circle. What does the circle tell you? Closed, right? In which case you can use Green's theorem. Okay, so here's what we are doing today. We are going to integrate over a smooth parametric surface. So what we have integrated over before was something like this. We called it a lamina. So we said it had very small height and the height was negligible. So now what we're going to do is we are going to integrate over a thin curved plate. Okay, so as it says above, we're going to have a parametric surface. So it's going to be defined like we have been defining. R is in terms of u and v. So you have some function, x in terms of u and v times I, some function in terms of u and v times j, and another function in terms of u and v times k. And this is going to be defined in the UV plane somehow. So this is our region D, let's say, that's defined in the UV plane. Like before, we're going to split this up into little pieces. And we're going to choose one box, let's say this one. We are going to label that specific box R of ij. This side is delta U, this side is delta V. R then is going to be some surface that is defined on that UV plane. This time, though, we're going to graph it in terms of x, y, and z. Let's say it looks something like this. We'll call that S. Again, we're going to split it up. This red box in D corresponds to the same red box in S. That box we're going to say is S of ij. And in that S of ij, we're going to pick some point, any point. Okay, so then what we're going to do is we're going to form the Riemann sum. That'll be the following. The sum from I equals 1 to m, and then the sum from j equals 1 to n of f of p of ij star times delta s of ij. It's important to know what that stands for. That is the area of the patch. That's going to help us later when we talk about how to integrate this, or how to evaluate it, rather. So then with all the Riemann sums, we always look at what happens as you take the limit, so as you get smaller and smaller intervals and more of those boxes. So if we take the limit as mn approaches infinity, the sum from I equals 1 to m, so the same sum that we just wrote down, here's what that becomes. Two sums, that's going to be a double integral. That's going to be f of x, y, z. That delta s becomes ds. And then you have an s down there. So the two indicators that this is called a surface integral, and the two indicators are the capital S here and d big S. And the fact that it's a double integral. If it were a line integral, it would be a single integral. So this is called the surface integral of f over S. So again, if it's a double integral with a big S, that's going to be a surface integral, not a line integral. Okay, so the big question that arises is how do we evaluate this then? Because that's not super helpful. There's a few different ways to evaluate. We're going to look at one of them. First way to evaluate, similar to a line integral, is if you parameterize the surface. So if we choose to parameterize, then that surface integral is going to become a double integral over the region D. Again, like we wrote above, D is the region in the UV plane. It'll be f of r of uv. And then we talked about how that delta, this right here, the delta s of ij, that was the area of the patch. So this will be the norm of ru crossed with rv dA. And that should make sense. You guys have seen this before. It's a surface area. Okay. Before we jump into an example, I want to tell you two important interpretations of a surface integral, or two uses of a surface integral. The first one is mass. Second one, if you do the surface integral of just ds without a function, that gives you surface area. So here's our first example. We're going to do the surface integral of x squared ds over the sphere S that is defined by x squared add y squared add z squared equals 1. Okay, first thing that we're going to have to do is we're going to have to parameterize this. Any ideas for parameterizing? Yeah, it's going to be spherical-like. It's not exactly spherical because we actually have a row. So x in this case will be sine phi cosine theta. Y will be sine phi sine theta. Z will be cosine of phi. So then we say that R is defined in terms of phi and theta. And again, we talked about with surface area, it doesn't matter the order that you put those in. So we are going to have to find R of phi crossed with R of theta, and then the norm of that. So this will be cosine phi, cosine theta, cosine phi, sine theta, negative sine of phi. So that's R of phi. If I want to do R of theta then, so the derivative with respect to theta, I get negative sine of phi, sine of theta, sine of phi, cosine of theta, and then 0. Okay, so we get 0 minus negative sine squared phi, so we get sine squared phi, cosine of theta. The next one we get 0 minus, but then we have to flip the sign because it's the middle term. So we get sine squared phi sine of theta. In this last term, we get sine phi cosine squared theta plus sine phi cosine sine squared of theta. Am I going too quickly, Brian?
It's 0 minus sine squared phi sine theta.
Which one are you talking about? The middle term?
Yeah.
Yeah, 0 minus, but then remember the middle term, you flip the sign. Okay, so this does simplify. The first two terms don't. Last term, you can factor out that sine phi, cosine phi, and you're left with cosine squared plus sine squared, so that'll be 1. So we had sine phi, cosine phi, which should look familiar because we found that yesterday. Not yesterday, day before. Now we need the norm of that. Okay, you can factor out sine to the fourth. You're left with cosine squared plus sine squared, which would be 1. So this gives us sine to the fourth of phi, add sine squared of phi, cosine squared of phi. And then if you remember yesterday, I factored out a sine squared phi. So you're left with sine squared phi plus cosine squared phi, which ultimately simplifies to sine of phi, which again should not be a shocker because we did that before. So here's where that takes us. That surface integral of x squared ds is going to be the double integral over the region D, which we're going to get to in a minute what that is. X squared is this squared, so that'll be sine of phi cosine of theta squared times that sine of phi, and then d phi d theta, or the other way around, doesn't matter. Phi goes from 0 to pi, theta goes from 0 to 2 pi. Okay, are we good on how I got to that point?
So we don't need like an extra term because we're converting to spherical?
No, because we didn't convert to spherical.
Okay.
We just used those coordinates.
Oh.
Okay, we can split this up, so I would suggest doing that. We'll get 0 to 2 pi of cosine squared theta d theta times 0 to pi of sine cubed phi d phi. Okay, so that first integral, we're going to have to replace cosine squared of theta. That's one that we've seen before. So 1/2 add 1/2 cosine of 2 theta d theta. Second one, if you consider that to be sine of phi times sine squared, you can replace the sine squared. So this is really sine of phi times 1 minus cosine squared of phi. Bless you, d phi. Bless you. So integrating on the first one, we get 1/2 theta, add 1/4 sine of 2 theta from 0 to 2 pi. You should be able to see that that just ends up being pi. For the second one, we're going to distribute that sine. So we get sine of phi, subtract sine of phi, cosine squared of phi, d phi. Which will be negative cosine of phi, add 1/3 cosine cubed of phi from 0 to pi. I plug in pi, I get 1 minus 1/3 minus -1 plus 1/3. Please have good notation. So like I have dots to indicate that I'm still multiplying. Don't just have numbers all over the place and then magically have them appear together at the end. That is 4/3, so we have pi times 4/3. So our final answer is 4 pi over 3. Okay. Questions on evaluating if you have a parameterized surface? No? Okay. We're going to talk in a minute about what you do if you have a rectangular surface, but there's one more use that we need to know for surface integrals. Another use is to find the mass or center of mass. Mass would be the not the double integral, the surface integral of rho of xyz ds, rho being the density. You would find x bar, y bar, and z bar then. I'm going to show you how to find x bar, and then y bar and z bar are very similar. X bar is 1 over the mass, again, times the surface integral, this time of x times rho of xyz ds. And then y bar, z bar are the same. Okay. So I told you there's a few different ways to evaluate. The first way is the way we just talked about, is if you have a parameterized curve. If you have a rectangular surface though, here's what you would do then. So your setup is still going to look the same. It's going to be the surface integral f of xyz ds. Okay, that'll become the double integral over the region D of f of x, y, and g of xy. Do you remember how to find surface area of a rectangular surface? Involves a square root. Partial of z with respect to x squared. Partial of z with respect to y squared plus 1. And then dA. Again, that shouldn't be a shock. Okay. So let's look at how to do that. We're going to take the surface integral of y squared at 2yz ds, where s is the first octant of 2x add y add 2z equals 6. Okay, you certainly could parameterize this. It's just extra work. If you were to parameterize, what would you do? Solve for z. Right, x equals x, y equals y, z equals whatever in terms of x and y. Okay, we are still going to need those z in terms of x and y. So the first thing that we want to do is we want to solve for z. Z is 1/2 the quantity 6, subtract 2x, subtract y. Based on our formula above, we're going to need the partial of z with respect to x, the partial of z with respect to y. Partial of z with respect to x is -1. Partial of z with respect to y is -1/2. So then if we do that square root, z with respect to x squared, z with respect to y squared plus 1, we will get 1, add 1/4, add 1, which is 9/4. Square root of 9/4 is 3/2. So then, this is going to become double integral over the region D, which we can take care of in a minute, of y squared, add 2y times z. So you plug in all the stuff you get for z. So that 1/2 6 minus 2x minus y times that 3/2 dA. So the 2 and the 1/2 are going to cancel. I'm going to pull the 3/2 out in front. So we're going to end up with y squared, add 6y, subtract 2xy, subtract y squared. So this will be 3/2 double integral of 6y subtract 2xy. And now we got to figure out the bounds. Okay, bounds is the region D, which is the region in the xy plane. So what we're going to want to do is we're going to want to graph this. What is this surface? A plane. So let's graph the plane. Only in the first octant. X-intercept is 3. Z-intercept is 3. Y-intercept is 6. Okay, so then D is this little region in the xy plane. So I'm going to draw that separately. So that's our D. Does it matter if we integrate with respect to x or y first over this region? No, there's not one that's going to be easier. I'm going to do y and then x just because that's convention. Y is going to go from 0 to the equation of the line. Equation of the line is 6 minus 2x. X then goes from 0 to 3. Okay. I think you guys can evaluate that on your own, so we're not going to go through it. If you want to know the answer, it ends up being 243/2. Okay. That is the beginning part of surface integrals. So remember when we learned line integrals, we learned the beginning part of line integrals, and then we talked about work, which was the main application. Now we're ready to get into applications. We can either start that now or wait until tomorrow. We are about 37% of the way through notes. So, do we want to keep going or do you want to wait until tomorrow? Okay, and we have the brain space and attention span to keep going? We'll find out. That's great attitude. Okay, so like line integrals, we talked about line integrals of vector fields. We're now going to talk about surface integrals of vector fields. When we took the line integral over a vector field, what information did that give us? Work. Right, I just told that to you. That's the one that looks like this. If you take the surface integral over a vector field, you end up getting what's called flux. Have you guys done that in physics? Not yet? Okay, so these are the two main applications when we talk about vector fields. Okay, So we're going to start with what's called a flow field. So think about f of x, y, z, so the vector field, representing the velocity of a fluid particle at the point x, y, z. Okay, before we get into how to actually calculate flux, there's some vocab that we need to go over. First thing we need to know is what is an oriented surface. Okay, there are two different types of surfaces. One is called orientable, and the other one is non-orientable. Orientable is a surface that has two sides. So generally one is called the inside and one is called the outside. This is what we are going to do in this class. We are not going to deal with non-orientable surfaces. A non-orientable surface, though, has only one side. Can you guys think of a surface that only has one side? Yeah, a Mobius strip. Okay, do you guys know what a Mobius strip is? Some yes, some no. Something like this.
Oh, yeah.
Right? So if a bug is, let's say a bug or a person or something is walking, eventually they're going to get into the middle. Does that make sense? Have you seen that before? Okay, great. Okay, so like I said, those are not the ones we're going to work with, though. We're going to work with the orientable ones. So let's say that this is our surface. N is going to denote a unit normal vector at each point. So here are all of our n's, or various ones. The opposite of that, then, is a unit normal in the opposite direction. So that'll be something like this. So there are only two options for the unit normal. Okay, one thing that's important to know is that those unit normals will never have an abrupt change in direction. So for example, you're never going to see something like this. So you're never going to see that all of these are n and then this is also n. That's not possible. You're not going to have that abrupt change. And here's why that's important. If we have an orientable surface, we need to know which one is the positive orientation and which one is the negative orientation. So this tells us that's not going to change. The direction for the positive orientation isn't all of a sudden going to change. The orientation of a smooth parametric surface is going to be defined by that n. So n will tell us the orientation of the surface. Any idea how to calculate n for a surface that is defined parametrically? You should be able to figure out the direction piece of it, at least. Think of a plane. If you have r defined in terms of u and v, what are two vectors that are definitively in the plane? Ru and Rv. So then which vector would be perpendicular to that? When you cross them. Yeah. So n will be Ru crossed with Rv over the magnitude because it has to be a unit vector. Okay, there are two names for this. One is sometimes this is referred to as the natural orientation. It's also referred to as the positive orientation. Okay. So we're going to look at orientation for a little bit. It is going to relate to flux, so this does come back to surface integrals eventually. Let's look at the surface r of uv that's defined by the following: cosine of u, comma v, comma negative sine of u. We are saying that u is defined by 0 to 2 pi, v is 0 to 3. What is this surface? What is it? Yeah, it's a cylinder. Yeah, it's a cylinder. You guys are right. Okay, so to find the orientation, we're going to have to do r of u crossed with r of v. So this will be I, j, k. So r of u will be negative sine of u, 0, negative cosine of u. R of v will be 0, 1, 0. So we get 0 minus negative cosine u, so just cosine u. 0 minus 0, so 0. Negative sine of u minus 0, so negative sine of u. Then we would have to find the magnitude. What's the magnitude of this going to be? 1? Yeah. Can you guys see that? Yeah. Okay. So our positive orientation then, our n, will be cosine of u, comma 0, comma negative sine of u. Okay, here's what that tells us. Let's choose the point where u equals 0 and v equals 0. So when we plug u and v equals 0 into here, we get the point 1, 0, 0. At that n, we get 1, 0, 0 as well. So this is the point 1, 0, 0. The vector 1, 0, 0 goes outward like that. It's payback for when I'm loud later in the day. Okay, so that's really important. What that tells us is that outward orientation is positive. So the natural orientation of the surface is going outward. Inward then is going to be negative. And again, that's not going to change abruptly. outward will always be positive for this surface. Okay, here's what I'm thinking. We still need to talk about how to calculate flux. Why don't we talk about how to calculate it, and then we'll leave the examples for tomorrow. Does that work? Okay, great. Wow, we took a lot of notes so far. Okay, all that orientation leads to flux. We need to talk about a few conditions before we talk about the definition of flux and how to calculate it. First condition, we will only deal with incompressible fluids, so fluids that have uniform density. Second condition is we are going to assume that the velocity of a fluid at a fixed point does not vary with time. This is called steady state. Okay, now we can talk about the definition of flux and how to calculate it. Flux is the volume of a fluid that passes through a surface in 1 unit of time. There's a few different pieces that impact flux. First one should be the most obvious, the speed of the fluid. The greater the speed, the greater the volume that's getting through the surface. Second one is how the surface is positioned relative to the flow. Okay, so there's kind of two different extremes. Let's say that this is our surface, and this is our flow. So in which case, the flow is parallel to the surface. In this case, the flux is 0. Nothing gets through. Does that make sense? If our fluid was flowing this way, right over our surface, nothing's going to get through the surface. Okay, logically then, do you have a guess for when the flux would be at a maximum? Perpendicular. Yeah, so let's say your surface was something like this, and your flow was perpendicular. This would be the maximum flux. Okay, there's one more factor that influences the volume that gets through. Do you have any idea?
Density.
Yes, the area of the surface. All right, larger area, there's going to be a larger flux. Okay, so how to calculate flux? First thing that you need to know is the symbol for flux. This is a symbol I use. I don't think your book uses, though. So anytime you see that in your packet, I use that to denote flux. So this is going to be the surface integral over the surface S of F dot d big S. This is how you know that we're talking about flux. Okay, this is going to be the double integral, not the double integral, the surface integral of f dot n ds